Now for trapeziums, and let me make some space for trapezium, we've already seen that to show that something is a trapezium just means that we've got opposite sides that are parallel. So I'll simply just show that the gradient of AB is equal to the gradient of BC. But then I get a special trapezium called a equilateral. Is that how you spell it? I think it's an I. Doesn't matter. Equilateral trapezium. Equilateral trapezium would mean that the two sides that are not parallel are equal. So let's draw equilateral trapezium. So equilateral trapezium, these two sides will be equal. Now, to be honest, we've already said that a parallelogram is a special trapezium, and a parallelogram is actually also a equilateral trapezium because it has these two opposite sides are equal and those two opposite sides are equal. But so obviously it is not, it could be, a equilateral trapezium could be equal in opposite directions. Notice how these two legs pan away from each other. It could also be that they are in that direction, but the moment they do that, if they're equal like this, it would be a parallelogram. So I'm not going to look at that one. I'm going to look at this one specifically. Nope, not. There we go. This is equilateral trapezium, where those two legs that's not parallel are equal to each other. So again, how would I show that? Well, I'll just show the two properties. The one property that that if this is a BCD, I will show that the gradient of AB is equal to the gradient of DC. Then I'll show that the distance between AD is equal to the distance between BC. So I'm really just applying the property. Cyclic quadrilaterals. Okay, in cyclic quadrilaterals, we are going to have to do the following. Cyclic quadrilateral has the following property that we are going to use to A, B, C, D. It has the property that opposite angles are supplementary. That means that opposite angles, well, this should be a D, I apologize. That means that if I add X and Y, okay, these are opposite angles, X plus Y equals 180 degrees. And so if this is X plus Y, let's call this S and T. S and T, opposite angles are 180 degrees. So to prove that something is a cyclic quadrilateral is actually quite a process, because what I'll have to do is I'll have to get the angle between, for example, I'll have to get the angle of A and I'll have to plus the angle of C. And if it gives me 180 degrees, it is a cyclic quadrilateral. So I don't have to show the other two as well. If any two opposite angles add up to 180, it's a cyclic quadrilateral. So how will I get angle A? That's the question. How do I get angle C? Well, we'll have to use the inclination of, so I would get, for example, for this one, I would have to get the inclination angle, which will give me that angle there, and the inclination angle for this one, which will give me that angle there. And so I'll get just as an example, sorry, I'm I'm rambling. Okay, so I will, for example, take theta as tan of the gradient, arctan of the gradient between A and B. This is just an example for this specific layout of these points, and that will give me this angle here. Okay, then I'll use this formula again, theta arctan and I should actually use a different color just so that it makes sense on the sketch. Theta equals arctan, and then get the gradient of AD. Gradient AD, that would give me this angle here. Okay, it's a negative angle. You can see it's going down, so it was a negative angle, so I'll just take the positive part of it and I'll add these two together to give me angle A, and now I've only gotten angle A. Okay, so I'll now have to go again and do the same thing for a C. Now C is slightly more difficult because if I draw, okay, I'll get this angle here. Okay, which is slightly a bit more difficult, but since I have that angle, there's another property. Maybe this property will be slightly easier to prove. If your opposite angles are supplementary, then the exterior angle, the angle on this side, okay, is equal to the opposite angle. That's another one. So that would maybe be easier to prove, but let me not do that then, since that is a whole lesson on its own. But okay, I'm going to get for C, I can get this angle right here, and then I can also get this angle right here, which is great if you already know the property that an exterior angle to cyclic quadrilateral is equal to the opposite and interior. Then you've already done that, because here you have the exterior angle, if you understood what I just said. If you don't, then obviously you'll add these two together, and notice this is a straight line. You'll add these two angles together that you've just found, and then you'll subtract it from 180 to find the angle inside here. Okay, and then when you subtract it from 180, if you now find that the angle that you got here and the angle that you've just calculated is supplementary, then you've got a cyclic quadrilateral. Great, let's finish up this lesson by looking at kites. Okay, a kite, as I've said, we've got that adjacent sides are equal, so obviously that is one thing you can do, is just show that A, B, C, D, for example, show that distance from A to B is equal to distance from A to D, and that's not sufficient because this one can still move around. Okay, so we also have to prove that the distance from BC is equal to the distance from CD. Okay, so this is the long way around, but if you know another property of the diagonals, okay, if you know the property of diagonals, if you can find that the gradient of AC and the gradient of DB is perpendicular, then you've also proven to show that it is perpendicular. In other words, if I can show the gradient AC is equal, multiplied to gradient dP is equal to -1. If I've shown this, then it has to be a kite. That's it. All I need to show is these two gradients multiply and they give me -1. Now you can decide whichever you think is easier, whether to do four distance formulas or multiplying two gradient formulas. Now just to mention this, that just because you've shown it's a kite, it could also be a rhombus, because a rhombus has the same quality that adjacent sides are equal. It could also be a square, because a square has also that property. So in other words, a rhombus will also have that its opposites bisect each other in a 90-degree angle, and the same goes for a square. Anything that has adjacent sides that are equal to each other. Adjacent means it's sides that touch each other, if you didn't know. So thank you very much for watching. This is as many as I'm going to focus on or show you. I know this is a long video. I've shown you a lot, but I do believe this is such powerful and simple applications of analytical geometry, and you will find it very useful. Thank you for watching. See you in the next video.